Chemical reactions can be intimidating, all those letters and numbers thrown together like an amalgamation of English and math that most students would consider an abomination. Today, let's try to demystify these monsters and see if we can better understand them. Looking at a reaction, you may see some things you recognize. Hopefully you can differentiate between individual elements and compounds. You are probably familiar with some of the numbers found in a chemical reaction. Subscripts, the little numbers, apply to only what is directly in front of them, and are used to balance the charge of atoms in a compound. So a compound like ammonium dichromate has 2 chromiums and 7 oxygens because of their subscripts, but it also has 2 nitrogens and 8 hydrogens because 2 times 1 is 2 and 2 times 4 is 8. Subscripts are distributed into polyatomic ions. You may even have an idea about the letters that come after compounds, which tell us about the state of matter of that compound. S for solids, L for liquids, G for gases. The one that is probably not familiar to you would be AQ, which stands for aqueous or in water. Compounds that have this notation have been dissolved into solution. We'll spend an entire unit discussing those later. For now, just being able to identify them is enough. We balance chemical reactions by changing the large number in front of the compound called the coefficient. Unlike subscripts, coefficients apply to the whole compound. So if I have 2 formula units of ammonium dichromate, I would have 4 nitrogen atoms, 16 hydrogen atoms, 4 chromium atoms, and 14 oxygen atoms. The law of conservation of mass says that matter can be neither created nor destroyed, so whatever you put into a reaction has to come out on the other side. Elements in your reactants can be rearranged and reformed to form products, but you can't change the identity of those elements. This means that, like math, what is on one side of an equation must equal what is on the other. So if we use ammonium dichromate in reaction, say by providing it just a bit of heat, it would break apart or decompose according to this reaction. Notice, however, that the number of hydrogens you start with and the number you end with are completely different. This means that the reaction is unbalanced and breaks the law of conservation of mass. Balancing this reaction may be a bit intimidating. Let's start with something a bit easier. Here we have the Haber process, a synthesis reaction, which is how ammonia in fertilizers is produced to this day. Atmospheric nitrogen reacts with hydrogen to produce the compound ammonia. Looking at an atom inventory of the products and the reactants show that this reaction is also unbalanced. We have 2 nitrogen atoms as reactants and 1 nitrogen atom as a product. So we ask ourselves, what times 1, the subscript, gives us 2? Clearly the answer is 2, so we'll change the coefficient of ammonia to 2. Now we have 2 nitrogens becoming 2 nitrogens. Our hydrogens, however, are still not balanced. To fix that, we'll again have to look at what we have. 2 hydrogens becoming 6 hydrogens. So what times 2, the subscript, gives us 6? 3. So we'll change the coefficient of the elemental hydrogen to 3, giving us 6 hydrogens on either side of the reaction. Notice that the only numbers I ever changed were the coefficients, never the subscripts. Changing the subscripts changes the compound. That's cheating and won't work. You can change coefficients to any whole number you wish, however when you are finished, make sure they are the lowest numbers possible. So for our example of the Haber process, 1 to 3 to 2 is as simple as it can get. Even though 2 to 6 to 4 would also balance the reaction, it would not be correct as it is not the simplest ratio of one element to another. Balancing reactions is a skill. Like any sport, the more you practice, the better you get at it. However, I do have some tips to help you along the way. First, keep polyatomics together. Look at the double replacement reaction between calcium nitrate and ammonium sulfate. Taking an atom inventory, element by element, would look like this. Obviously, it is unbalanced, but you now have a massive laundry list of elements to go back and balance. However, look at those elements. In the reaction, they appear together in the same ratio both in the reactants and in the products. This is because there are polyatomic ions present. They are going to stay together. If a polyatomic ion is on the left and right side, treat it as though it were its own element. Instead of saying I have 2 nitrogens and 6 oxygens, say instead that I have 2 nitrates. Reworking our atom inventory with that in mind simplifies things a lot. Now just go through and balance your reaction. A quick side note to this is water and hydroxide. If water and hydroxide are on opposite sides of a reaction, rewrite the water as hydrogen hydroxide. This will make balancing your hydroxides much easier and will come in real handy when we get to acid-base chemistry. Balancing is also made much easier if you save anything elemental, one capital letter, for last. For example, the combustion of octane. Here, you should start by balancing carbon and hydrogen atoms, and save oxygen for last since it is elemental. So we'll first need 8 carbon dioxides and 9 waters to balance the 8 carbon atoms and 18 hydrogen atoms in octane. Next we'll look at oxygen. Adding up the oxygen atoms on the product side of the reaction, we find that we have 25 oxygens. Now I don't know about you, but I don't know any whole number that multiplied by 2 will give me 25. So I'm stuck, which is my final tip. If you are ever stuck with just one element or compound out of whack, double everything and leave that element or compound blank and come back to it. If that doesn't work, triple everything except for that one element or compound. If we double everything except for oxygen, we reevaluate and carbon and hydrogen are still balanced. However, we now have 50 oxygens on our product side. So what times 2 gives you 50? 25. And just like that, we've balanced a combustion reaction. Again, balancing is a skill that takes lots of practice to even be reasonably good at. Your teacher or professor will hopefully give you a lot of practice with this. But if not, you can Google balancing problems or worksheets and you will undoubtedly find a lot of examples. Remember, the more you do, the easier they will become. Use the tips, keep polyatomic ions together and save elemental compounds for last, and you will be well on your way to being a balancing master. Thanks for watching. In our next video, we'll talk about stoichiometry in 3 ways. If there's something we mentioned in this video that you didn't quite understand, perhaps it was in our previous video. Diatomic molecules and percent composition. Special thanks to the following websites for their clip art and cartoons. Please don't sue me, I'm just a teacher. Also, a special thanks to Renee McCormick of the National Math and Science Initiative for her videos, which I have done a very poor job of boiling down to under 5-minute segments, as well as her curriculum and notes. A link to her videos and the notes can be found in the description below. See you next time.